If you remember in lecture 40, we ended with example 5, and we said that we wanted to get familiar with the laminar flow and how we can apply derivatives in laminar flow. And then we had nice problems like this, and then we had a diameter there which is 0,016, and then of course, and then after that we had this question and this nice question, and we said that in order for us to really understand, we need to cut an artery and then look into it as a cylinder, and then use the law of laminar flow, which is like this, and we can answer these problems. The first problem was just for us to just plug in the value in a calculator. In most cases, when I'm just evaluating, I don't usually take this the final answer serious, but I want you to get to understand the concept of what is happening. You plug it in, and then secondly, and if you can even notice there, when we are getting this this value here, we had a diameter which was 0,016, therefore the radius was supposed to be half of that, or 0.016 divided by 2. And if you realize this, it was supposed to be 0,016, and then you divide it by 2, and then after that this is supposed to be instead 0,008. That's what it's supposed to be, because having a 3 here is just saying that I'm moving a comma 3 times to get an 8. So that is what was supposed to happen here. So the value here was actually supposed to be 0,008, and then you square it up to get this value here. And also another thing that I don't want you to be thinking much more about, say we have 0, something, but we don't have a calculator when you're writing an exam. This problem I was trying to give you realistic problems. Of course, when you're dealing with the realistic problems, you usually deal with problems that usually needs you to have a calculator. But when you're writing an exam, you don't really you're not gonna get problems that are this kind, because these ones really need a calculator. It's not like you cannot solve these problems. You can actually solve these problems by just realizing that for instance, to change this, you can change this decimal to a whole number and just multiply by this one is 1, 2, 3. So I can just multiply this whole thing by 1000, and then multiply by 1000 in the numerator, and then deal with that, and then I can deal with it. And also here I can do the same thing, so that I can get numbers and then find the common factors. Of course, it was going to be long, and for the video it was going to be causing it to be even much more long than it is. So that is why we're just focusing on a calculator. But in the test, like I said, you will get problems that don't want you to really use a calculator, and if we're giving you that problem, we expect you to be able to answer the question without a calculator. And also another thing that I want you to realize here, just for notation wise, the first derivative with respect, if let's say I want the first derivative of this with respect to r, this is just the same as the change in VR with respect to r, and you take the limit as data r goes to 0. I hope you can understand now the use of limits. And of course, this very same thing is the same as just dr of v of r. So let me write it so that you can see. This is just the same as just dr, because this is the independent variable which is there, and then of course inside we have v of r. So we're taking the derivative of that. I wanted you to also know that. And also another thing, if you look into this, another notation that is usually used is that if you are looking for v prime of 0.002, this is just the same if you are using, let's say you're using this notation here, is the same as d v, where v is this, and then with respect to r, but now we have a long line there, and then we write this thing here 0.002. so this thing here is the same. I just wanted to highlight that notation, and also I hope you get this. And also I don't want you to get hung up on this, that this there's a mistake here, supposed to be 0. I mean, it's just these problems are just highlighting how you're supposed to do this. So that is the main goal for this. And also, if you happen to deal with these problems in the future, at least you have an idea of what is happening. So today I want us to talk about L'Hopital's rule. And of course, L'Hopital's rule was first discovered by Bernoulli. Is Johann Bernoulli, and then after he has discovered it, of course, there was L'Hopital's who wanted to acquire the rights of Bernoulli's mathematical concepts, and they ended up having a very intriguing business arrangement to other people, because others, like, you can sell your work, and others you can buy work, something of that nature. This is not about saying this is wrong or right. I want you to just be aware that the person who actually discovered this was actually Bernoulli, and then L'Hopital's acquired the rights of that mathematics, and then he started to include it in his textbook, and then we know it as L'Hopital's rule, even though it was discovered by Bernoulli. And then, of course, if you wanted to know more about what that arrangement and all the information, this is where you can actually go. Harvard Eves in Mathematical Cycles, Volume 2, Quadrant 3 and 4, Boston, Pingley, Weber, and page 20 up to 22. But of course, this is just a nice background about this. I want us to actually look at what this L'Hopital's rule is actually saying. So we have L'Hopital's rule. It's not Hospital's rule, it's L'Hopital's rule. So we have the L'Hopital's rule. What is L'Hopital's rule is saying is this: suppose f and g are both differentiable functions. So they are both functions and they are both differentiable, and g prime of x, the derivative of this at x, is actually not equal to 0 near x is equal to a. It is actually not 0 except possible at x is equal to 0. So close to this value, it is not equal to 0. It might happen that it is 0 at that point, but close to it, it is not 0. And also, we suppose that the limit as x approaches a of f of x is equal to 0, and the limit as x approaches a of g of x is equal to 0, or the limit as x approaches some a of f of x is equal to plus or minus infinity, and the limit as x approaches a of g of x is equal to plus or minus infinity. So what we're actually looking for here is that I want you to notice that first, this function and that function must have a derivative, and also these two functions must be differentiable. And then thirdly, when I'm taking the limit close to this value or that value, I either get both zeros, or I get infinity and infinity, or positive infinity and positive infinity, or negative infinity and positive infinity there, or positive infinity that side and negative infinity there. In other words, we have an indeterminate form. We have an indeterminate form of type 0 over 0. So we either have indeterminate form of 0 over 0 or infinite over infinity. Then the limit as x approaches a of f of x, and then you divide it by g of x, is just the same as the limit as x approaches a of f prime of x divided by g prime of x. That is what L'Hopital's rule is saying. This is only going to be possible if the limit exists. Limit on the right exists, or I have the limit is either positive infinity or negative infinity. So basically, if this limit exists, we know that it should be the same as this. I talked about this, and then I said I don't want you to confuse the quotient rule with the L'Hopital's rule, because the L'Hopital's rule is saying that if it happens that when I'm taking this a and I'm plugging it in there and there, I get a 0 over 0 or infinity over infinity. All I need to do to solve this limit, the first thing that I need to do, I need to take the derivative of this with respect to x, and also take the derivative of this with respect to x, and then just take the limit. This one here, I don't want you to think that it is the same as the quotient rule, because you remember quotient rule, it was a rule that we used to take a derivative of the quotient of two functions. So please don't make that mistake and assume that these two things are the same. Quotient rule is different, low d high minus high d low divided by low low. But this one is just take the derivative of only the numerator, which is that, take the derivative of the denominator as this is that. In other words, this is a separate function and this is a separate function, and when you are taking the derivative, you just take the derivative of each. So let me write this so that you can, if you forgot, you can go back and look into it. Do not confuse the L'Hopital's rule with quotient rule. So that's what I was saying here. Now, let us take some examples. Maybe you will see this whole thing, how it works, because now this is just notation, and sometimes you don't even see what is basically happening here and all that stuff. Let us start by taking some nice examples here. I've compiled a few examples, and I think I have enough. So the first one here that I want us to look at is this. Let me first write this. Examples. So what I want you to actually do, I want you to evaluate the following limits. So L'Hopital's rule is under application. I usually add it under application of derivatives, because we are using derivatives to actually solve some of the limits. So I usually put it there. Others put it aside as a separate topic. So it's just a matter of preference. I don't think there's anything wrong or right with that. It's just a matter of preference. So we have this. So if it happens that you don't see it with your course outline, because some people usually say, I don't see it within my course outline, it is actually there. Let me double check. Yeah, take this out. So when you are looking into this, you will find out that these are the topics that are remaining. So I'm still dealing with applications. So if you look at applications, so I usually place it there, so it is under there. And then after that, we look at local, extreme, and maxima and minima, and then we go all the way. And we want to make sure that we cover these things before your test 2, so that at least you will be having enough information about some of the topics that you will be seeing in your test 2. So I'm just finalizing here, and then we'll go there. So that's where the L'Hopital's rule is actually is. So evaluate the following limits. So the first one here is one of the limits that we did. The limit as x approaches 0 of sine of x divided by x. So I want us to actually evaluate this. So what is important with this thing here, this a here, this a can either be a finite number, or this a can actually be infinity. So when I'm actually writing this whole thing here, I am actually not only emphasizing a finite value, I'm also even talking about infinity, if we were allowed to plug in infinity. And I've been saying this thing all over and over again, because most people saying you can't plug in infinity. Infinity is a concept. I understand that, but in order for us to get used to these limits, I usually say that let's assume that we can grab some infinite and plug it in there, and then we get some value. So this a, I usually also assume that we can assume that our a is infinity, or it can be negative infinity, or it can be a finite value. So when we are dealing with these examples, if we are seeing infinite, I don't want you to feel disturbed. I'm also assuming that a can be infinity. So if you take this 0 and you plug it there, we know that sine of 0 is just 0. You can even check here. So if I'm plugging in a sine of 0, it is 0, so we have 0. And then x, if I'm plugging in a 0 here, I am getting a 0 over 0. And this L'Hopital's rule want two things. Is either we're getting a 0 over 0, or we're getting an infinite over infinite. Any of the two is still fine. We can use L'Hopital's rule. So because I am getting a 0 over 0, this limit actually is going to be the same as the limit as x approaches 0. And then what is the derivative of that? I'm going to take the derivative with respect to x of sine of x, and then I divide this by the derivative with respect to x of just x. Of course, I still have the limit as x approaches 0, and then the derivative of sine of x is the same as cosine of x, and then the derivative of x with respect to x is the same as 1, and then after that I plug in a 0 there. So if I'm plugging in a 0 there, I end up getting cosine of 0, which is the same as just a 1. You remember when we were using the squeeze theorem to solve this thing, with L'Hopital's rule, you can solve it as easy as this. That's how easy this thing is. It's not that hard at all. And then let's go back now to number B. Our number B was saying that evaluate the limit as x approaches 0 of cosine of x minus 1, and then you divide this whole thing by x. So if I'm plugging in a 0 here, cosine of 0, I know that it is 1. So cosine of 0, I know that it is just a 1. So 1 minus 1 is 0, so I'm getting a 0 in the numerator. In the denominator, I'm plugging a 0, I'm getting a 0 over 0. Since I'm getting a 0 over 0, which means I can use L'Hopital's rule. In other words, this is going to be the limit as x approaches 0 of d with respect to this here, so with respect to x, and then I have cosine of x minus 1, and then divided by the derivative with respect to x of just x, which is in the denominator. And then of course you can see that we still have the limit as x approaches 0, and the derivative, of course, you know that it is minus sine of x, and the derivative of minus, and the derivative of 1 is just a 0. Derivative of a constant is always going to be a constant, and the derivative with respect to x of x is just a 1. So this whole thing is going to be the limit as x approaches a 0 of minus sine of x. Of course, when I'm going to plug in there, I'm going to drop the limit, so I'll end up having minus sine of 0, which is just the same as minus sine of 0. We know that it is just a 0. And even if you look here, if let's say you forgot shift, you wanted the derivative of course this calculator cannot do what I want it to do. I was going to look at the derivative of cos. What's this? Derivative of cosine of x, and now I wanted to evaluate it at x. Of course, x is equal to I don't think this is going to actually do it. Yeah, it just want a value. I think it just want a value here. So here I'm just gonna plug in that 0. Shift. So this one is supposed to be cosine of let me do this, and then here I wanted to have this, and then I'm gonna let me try and put this. I don't know why this is not doing it. Okay, of course, if I'm actually taking the derivative of this, is supposed to be, if I'm evaluating it at 0, I'm supposed to get a 0, which is that 0, because I ended up doing that. Yeah, so that is actually what is happening here. The derivative is supposed to be that. I don't know why. Maybe it's not built like that, but you still remember that the derivative, of course, is minus sine. That is what is important. I have this. We were using L'Hopital's rule, squeeze theorem, to use this to solve that, if you still remember when we were dealing with the squeeze theorem. And then number C is saying, I want us to evaluate the limit as x approaches 0 of e to the power x minus 1 all over x. So how do you evaluate this? If I were to plug in 0 here, I would get this e here. How do I get it? It's supposed to be e, and then raised to a 0 there. You know that is going to be a 1. Let me start with that. So if I'm plugging in a 0, I press here, I press this e. First I have to start here. I press this e. If I'm pressing shift and then pressing this, I will see a pi. So I press an alpha to see an e. So I will end up having this e here, and then I want to raise it to 0. So I have 0, and then I'm separating a 1, and then I divide by a 0. You will see that because this one is going to be 1 minus 1, and that's going to be 0 over 0. We know that is going to say you are crazy, I can't solve that. So we're supposed to actually get a 0 because e to the power 0 is the same as 1. So 1 minus 1 is 0, and then 0 over 0. So we end up having 0 over 0. Because we are getting a 0 over 0, which means we can use L'Hopital's rule, which means that take the limit as x approaches 0, take the derivative of the numerator with respect to x, e to the power x minus 1, and then you divide it by the derivative with respect to x of the denominator. So if you look carefully into this, you will find out that you have the limit as x approaches 0. The derivative of e to the power x is the same as e to the power x minus the derivative of a constant, we know that is just a 0, divided by the derivative of x with respect to x, or the gradient of the function y is equal to x is just a 1. Of course, now I just plug in. When I'm plugging in, I drop the limit, so I end up having e raised to 0. Okay, let me first write this cleaner. So I have the limit as x approaches 0 of e minus 0 is just e to the power x, divided by 1 is just e to the power x. Therefore, when I'm dropping the limit, I'll just get e raised to 0, which is just the same as 1. Remember, when we're doing the squeeze theorem, we had to find functions. One function was x plus 1 less than or equal to e to the power x, less than or equal to x times e to the power x plus 1. And then we had the other one is either you used this to use squeeze theorem, or you said x plus 1 is less than or equal to e to the power x, and then we said it's less than x squared plus x plus 1. Either we used that, and the other one was actually using 1 over something, or x plus something. I think I forgot what we used, but these are some of the functions that we used. But with the L'Hopital's rule, all you need to know is that if you are plugging in a 0 there and you're getting a 0 over 0, then you can just take the derivative of the numerator, derivative of the denominator, and then evaluate the limit later. Sometimes you will find out that you have to take the derivative twice to actually get the limit, but it's still fine. I want you to understand that first of all, you plug in, and then if you're plugging in, you're getting a 0 over 0 or infinity over infinity. It's still fine. You can just use L'Hopital's rule. Of course, this one was just e to the power 0, which is equal to 1. Let's go to D. Our D now is starting to get a little bit interesting, because we are getting D, and this one is supposed to be the limit as x approaches 0 of 9 to the power x minus 5 to the power x all over x. If you remember correctly, this is the one of the limits that I kept showing you in class, that all the other methods that we have proved cannot actually solve this. Now I want to see if the L'Hopital's rule can actually help us to actually solve this particular limit here. Of course, this is going to be the limit, but what is important here, what will happen if I were to plug in 0 here? If I'm plugging in a 0 here, 9 to the power 0 is 1. And if I'm plugging in 0 here, I will get 5 to the power 0, which is 1. So I'll have 1 minus 1, which is equal to 0. So I am having a 0 in the numerator. And then if I'm plugging 0 in the denominator, I get 0 over 0. So I can use L'Hopital's rule here, which means that I will have the limit as x approaches 0, which is that. And then I take the derivative with respect to x of the numerator, which is 9x minus 5 to the power x. And then you divide this whole thing by the derivative with respect to x of x. So once you are actually having this, you still have the limit. You only drop it when you are finally plugging in. So what is the derivative of 9 to the power x with respect to x? When we were doing the derivative of the exponential functions, we said that you keep this thing as it is, so you will end up having 9 to the power x, but there must be a ln close to it of this constant here. So we end up having ln of 9 minus, and then here you will end up having 5 to the power x, and you must have a ln, and then you have a 5, which is that constant in front, and then you divide this whole thing by, if you actually look carefully into this whole thing here, you will find out that in the denominator, we're actually having the derivative with respect to x of x is just a 1. Of course, this whole thing is just gonna be the limit as x approaches 0. Dividing anything by 1, you're still gonna get that thing. So we still have 9 to the power x ln, and then you have a 9 there, minus you have 5 to the power x, and then you have a ln of 5. Of course, now we no longer have a denominator. If we don't have a denominator, then we have minimized the problems that we are actually having. So we try and plug in again and see what we are getting here. So when we are plugging in, we drop the limit unless otherwise we are getting a 0 over 0 or a number over 0, whereby we know what we need to do. So here I'm plugging in a 0. I will get 9 to the power 0 times ln of 9 minus 5 to the power 0 times the natural log of 5. Of course, 9 to the power 0 is 1. 1 times ln of 9 is just ln of 9 minus, and then here is the same, 1 times this 5 to the power 0 is 1, and then 1 times ln of 5 is just going to be ln of 5, because that's what is actually happening. And then from there, you know that whenever you have let me write here, whenever you have a log base a of x over y, this is always going to be the same as log base a of x minus log base a of y. And once you have a minus, when you're having a log rule, it means that this one is supposed to be in the numerator and this one is supposed to be in the denominator. That is why I said this is the same as ln of 9 over 5 when we were in class. That's what I said. So this is what is actually basically happening here. So we just use L'Hopital's rule. Of course, if you like the squeeze theorem, you can try and use it and keep looking at different functions. What are the functions that are going to help you so that you actually end up getting this? So this limit, you go like this and you end up here. And then let's go to number E now. Number E is saying that I want you to evaluate the limit as x approaches. Now I'm switching the gears. I'm not using 0, I'm using infinity, of e to the power x divided by x squared. So basically what is important here is this. This number can be 1, it can be 2, it can be 5. It doesn't need to be a 0, because sometimes you find out that if I'm plugging this number here, I'm still getting a 0 over 0, infinity over infinity. As long as we are having that part of the equation, you just have to do what needs to be done. If you look into this here, what is important about this is that when I'm getting e to the power infinity, I wanted to evaluate this function. What is this function as x increases unboundedly? Or if I were to plug this, because this is a constant, a positive constant raised to infinity, of course that is going to be a very big number, which is infinity. I know that. Or this function here is increasing unboundedly to positive infinity as x increases to positive infinity. And if you look into this one here, you know that this is infinity squared is the same as just infinity times infinity. A big number times a very big number is actually going to give you a big number. So what is basically happening here, I am actually having infinity over infinity. So I can use L'Hopital's rule, or you can think in terms of a function that this function is actually increasing like that. So as x keeps increasing unboundedly, the y values keep as x increases, the output, you can see that it is increasing. So as x keeps going this side, y is actually going to positive infinity. So we're having infinity over infinity. So when we are having that, all this thing says is that we have infinity over infinity. Since we are having infinity over infinity, it means that L'Hopital's rule can actually be used. So that's what we're actually going to do here. I'm just gonna say that this one is the same as the limit as x approaches infinity of the first derivative of e to the power x, and then this whole thing here, we want to divide it with the first derivative of x squared. Of course, this nice thing here is just gonna say to us that we let me first deal with this, because this is a solution. I want to do that because this is a solution. I want to change it. Of course, this one doesn't want to change. I don't know why, because it's supposed to be like that. And this one, yeah. And then after this, you still have the limit. You only drop it when you are plugging in. And then here, what is the derivative of e to the power s with respect to x? So this one is still going to be e to the power x because it does not change. It's only changing when this constant is different because you end up having ln of that constant. And of course here, even if you are saying this is going to be ln of e when you're taking the derivative of that, ln of e is the same as 1. That is why we don't put it when we are having an e. But if it's a different number, we put it. And then here, what is the derivative with respect to x? Is going to be 2 x. That is the derivative. So what is important here is this. When we are actually taking the first derivative of each of these two functions, we want to see which function is increasing faster at infinity. That is what is happening here. If this function is increasing faster than this one, then this limit will end up getting to 0. But if this function is increasing faster than this one, and then this limit will end up getting to positive infinity or maybe negative infinity depending on the sign. So that is basically what is happening now. So if you look here, if I were to plug in infinity here, I would still get, if I plug in infinity, I will get e raised to infinity divided by 2 times infinity. So here, you can see that this function is a function that increases like this. So it keeps increasing as x increases. So this one is actually going to infinity as x increases. Or a constant, a positive constant raised to infinity is always going to give you infinity because this is a determinant form. And then this one, a constant times infinity, a positive constant times infinity, we know that it is infinity. So we are actually having another indeterminate form. So we have infinity over infinity, which means that we can use L'Hopital's rule once more to actually evaluate this limit, which says that we can find the first derivative of e to the power x divided by the first derivative with respect to x of 2 of x. So this whole thing is going to be, what is the derivative of that? We still have the limit, of course. What is the derivative of that? The derivative of e to the power x is the same as e to the power x, and the derivative of 2x with respect to x is just a 2. And now what we actually do, we try and see if we can plug in. And if we are plugging in, we get e raised to infinity over 2, which is the same as, we know that this one is increasing faster. So if it is increasing faster, or it is a positive constant raised to infinity, the same as infinity divided by 2. And a constant, infinity divided by a finite positive number, we end up getting infinite. I mean, you cannot reduce infinite by dividing it. But if this one was a negative number, we're going to end up with negative infinity. So that is what we are actually end up with here. So we are in a different number there. I hope you can see here that we took the first derivative, but still we got an indeterminate form. So we applied the L'Hopital's rule once more, and then we ended up getting a nice thing, which is like that. And then we're dealing with e. And also another thing that is important I want to highlight here, because we are ending up with infinity, it means that at infinity this function is increasing faster than that function because we are ending up with infinity. If we were getting a 0, it was going to mean that this function is actually increasing faster than that. And of course, you can notice that if you were to switch this to be in the denominator and this one in the numerator, would end up having a limit that is going to be evaluated to 0. Now let us take another function here, f. We want to find the limit as x approaches infinity of natural log of x, and then we divide it by x raised to some constant a, where a is greater than 0. So that is what we wanted to actually see. We know that our a is actually getting to 0. Now if I were to plug in infinity here, we know that a natural log function is increasing like this. So as x approaches a positive infinity, we have our y. You can see that if I pick a value here, we have this, pick a value there, I can see that I'm going that way. If as I keep picking values, if I pick another value somewhere there, you can see that I'm going all the way. I pick another value there, you can see that I am getting to some value there. So as x gets to positive infinity, y is also getting to positive infinity. In other words here, natural log of infinity is just equal to positive infinity. And then if I divide that by x to the power a, we know that once I have a to the power, this is a power function, and we know that power functions are always going either like this, or they go like this, or something of this, something of that kind, something like that. So as x keeps increasing, this function is always going to be increasing regardless of the value of x. So this one is also going to infinity. So when this one is going to infinity, this one is also going to infinity. So because that is happening, it means that we can use L'Hopital's rule, which says that this is supposed to be the limit as x approaches infinity of the derivative with respect to x of ln of x, and then you divide this whole thing by the derivative with respect to x of x to the power a, right? So basically, once you have that, you will find out that we're still gonna have the limit as x approaches infinity. And then when you look now into this, you will find out that what is a derivative of a natural log? We know that is going to be 1 over x. We always know that. So it's just 1 over x. That's what we did last time. And then the derivative of this, we know that is going to be the constant a times x raised to a minus a1. So that is what is happening using a power rule. So this is going to be the limit as x approaches infinity. I want to clean this whole thing up, and you can see that this thing is actually saying that we have 1 over x, and then I have, because this one is in the denominator, so I also have a 1 over x times 1 over a times x raised to a minus 1. So that is what is happening here. Or if you don't want it to see it like that, you are thinking that how did we end up with something like that? This one here is actually a divide. So we are actually having 1 over x divided by a times x raised to a minus 1. And if you notice here, there is also a 1 there. So when you are dividing with a fraction, what you usually do, you just interchange the numerator. So I'm changing this division to multiplication, so the denominator becomes a numerator and the numerator becomes a denominator. I still have x minus a. So if you look carefully into this, this is the same as the limit as x approaches infinity of 1 divided by, I have a, and then times x, I have an a there, and then after that I also have minus 1, this minus 1, and then when multiplying powers of the same base, I have an x and I have an x there. So you add exponents, there was a 1 there, so I'm going to add a 1. So this whole thing will end up becoming the limit as x approaches infinity of 1 divided by a times x raised to 1 minus 1 or minus 1 plus 1. We know that it's a 0, so we end up having that nice a there. And then because we are having this nice thing here, what is also important is this. This now I'm going to plug in. So when I'm plugging in, I drop the limit, so I'll end up having 1 divided by a times I'm going to have some infinity raised to a positive constant. So once I have a positive constant here, this is going to be infinity. Of course, we said it's going to be 1 divided by a times infinity. this is positive. A positive constant times infinity is going to be positive infinity. So I have 1 over infinity, and then 1 over infinity is just a 0. So that is what is important in this particular case. I hope you can see what is happening here, that we take the derivative of the numerator, take the derivative of the denominator. And then we are now in number G. Number G is saying I want to evaluate the limit as x approaches infinity of x times e raised to minus x. Of course, if you look into this, I want you to just realize that once you have something of this nature, I have a negative exponent. The negative exponent means this whole thing is positive in the denominator. So I will have x, and then I will divide this by e to the power x. And if I plug in infinity here, I will just end up having infinity. If I plug in infinity here, I will end up having e to the power infinity, and we know that a positive constant raised to infinity is just gonna be infinity. So I have infinity over infinity, which means I can use L'Hopital's rules and say that I'm looking for the limit as x approaches infinity of this. Now I take the derivative of that with respect to x and I divide this. I take the derivative with respect to x of e to the power x. Of course, you know that the derivative of e to the power x of x, I mean with respect to x, is just gonna be the same as dx, or just a 1. So we have the limit as x approaches infinity of 1 divided by this. The derivative of this, we know that it is just e to the power x. There is nothing that is going to change there. And if you notice something here, which means that this function is increasing faster than that at infinity, and then we drop the limit, and then we plug in infinity in the value of x, and then when we're plugging in, we know that a constant, positive constant raised to infinity is the same as just infinity, and 1 over infinity is the same as a 0. That is what is important here. I hope you can catch up and you can actually get this thing, because it's not that hard. What is important is that make sure that you are actually familiar with the rules that we did when we were looking at the limits at infinity. Now another example will be at h. We want to evaluate the limit as x approaches infinity of e to the power x plus x to the power 3 all over e to the power x minus x to the power 5. Basically, we wanted to see which of these functions is increasing faster between this one and that one, and by how much. So at infinity. So if you look into this one here, if I were to plug in infinity here, I want you to see something. Here I would end up getting this would go to infinity, and this one here will actually be also infinity, and then infinity plus infinity, that will be infinity. And when we are dealing with the denominator here, we know that if I take the derivative of this function, I will get this, the same thing. But if I keep taking the derivative of this, when I'm taking the 6th derivative, this one will be 0, but the 6th derivative of this will be this, which means that this function is actually increasing faster than that function at infinity, because this one is not going to be 0 anytime. It will keep getting the same thing. Therefore, here we'll get infinity over infinity here. That is why we can use L'Hopital's rule and say the limit as x approaches infinity of the derivative with respect to x of e to the power x plus x cubed, and then you divide this whole thing by the derivative with respect to x of e to the power x minus x to the power 5. And if you continue in this particular fashion, you will get the limit as x approaches infinity. The derivative of this is still going to be the same thing. and the derivative of this thing is going to be 3x squared, and then you go to the denominator. The derivative of this is going to be e to the power x minus the derivative of this is going to be 5x to the power 4. And if we are plugging in, we're still gonna get the same thing. That is why we apply L'Hopital's rule once more, and we take the derivative of what is happening in the numerator with respect to x, and we have e to the power x plus 3x squared, and then you divide this by ddx of e to the power x minus 5x to the power 4. And if you look carefully into this, you will find out that we end up with the limit as x approaches infinity. And then this part over here, what is the derivative of this? We're still gonna get the same thing, and then plus, and then the derivative of this is going to be 2 times 3 is going to be 6x, and then in the denominator we're still gonna have e to the power x because the derivative of this is still gonna be the same, and then minus what will be the derivative of this. 5 times 4 is going to be a 20x, and then we reduce 1 there, and then we have a third. And then lastly, you see that when you're plugging infinity here, I'm still gonna have infinity plus infinity infinity, and this one here you can see still there, and this one keeps reducing the power there, so we can see this one is increasing faster than that. Of course, we can just look into this and say that we will actually be getting infinity from here, so infinity over infinity, which means that we can use L'Hopital's rule once more. So this thing here is going to be the same as the limit as x approaches infinity, and then here I am going to take the derivative with respect to x of the numerator plus 6x, and then I am going to take the derivative with respect to x of the denominator, and then I have 20x cubed, and then of course I proceed. I still have the limit because I haven't plugged in. We only drop it when we're plugging in, and then the derivative of e to the power x is the same as e to the power x plus the derivative of 6x. We know that is going to be 6, and then the derivative of e to the power x is going to be e to the power x minus the derivative of this is going to be 20 times 3, that's just a 60x squared, and then of course I reduced a 1 there, and then I multiply this exponent by that, and then we get this. And then when you look into this one here, you can see in the numerator I still have infinity, because infinity, I mean e to the power infinity, just infinity, infinity plus 6 is just infinity. In the denominator you can see that this one is increasing faster, because this one, every time we're taking a derivative, this one we are actually not getting there. And also you see now that we can actually see that we can still take the derivative once more. I mean the L'Hopital's rule once more. We take the derivative with respect to x of e to the power x plus a 6, and then we divide this by the derivative with respect to x of e to the power x minus 60x squared. Of course, if you look into this derivative here, you will find out we are having the limit as x approaches infinity. The derivative of e to the power x is e to the power x. The derivative of 6 is just a constant, so the derivative is supposed to be 0. And then the derivative of this is going to be the same thing, minus what is the derivative of this? We take this exponent, multiply 60, we get 120. Hope I'm right. We have 60 times 2, we are having 120, and then we have x, and then we reduce a 1 there, and then we're just gonna have a 1 there. And we can see that we still have infinity over and infinity there, so we end up saying, okay, let us take the limit as x approaches infinity of this whole thing here, but because we are getting infinity over infinity, we take the derivative again for the last time or last 2 times, and then we'll get e raised to the power x, and then plus 0 is just e to the power x, and then we take the derivative of the denominator with respect to x of e to the power x minus 120x. And if you look carefully into this, you will find out that now we are landing with the limit as x approaches infinity, And then looking into this here, what is the derivative of e to the power x is e to the power x. And then what is the derivative of e to the power x here is e to the power x. And what is the derivative of this part here is minus 120 because x is equal to 1. And this number here is way too less compared to infinity. So this one is driving and that one is driving. In other words, if I'm plugging infinity, I will get infinity. And when I'm plugging here, I will get infinity. And this one is actually increasing faster than that, which means that, and this one here, this is going to be leading. So we're having infinity over infinity. So let us take the derivative for L'Hopital's rule for the last time. Limit as x approaches infinity, and then we take the derivative with respect to x of e to the power x, and then you divide this by the derivative with respect to x of e to the power x minus 120. And if you look carefully into this, is going to be the limit as x approaches infinity. The derivative of e to the power x is going to be e to the power x. The derivative of e to the power x is going to be e to the power x minus the derivative of a constant 120 is going to be 0. And then this is going to be the limit as x approaches infinity of e to the power x divided by e to the power x. And e to the power x and e to the power x, they cancel out. Now you are having the limit as x approaches infinity of this divided by that is just a 1. And the limit of a constant is that constant. So what we're looking for here is actually we're trying to calculate 1. So how many times did we take a derivative? I don't know. We took it for several times. I mean, L'Hopital's rule, we applied it several times. So I want you to understand that you can take L'Hopital's rule more than 2 times. Sometimes more than 3 times, because you saw in this previous case. Let us look into this one here, which is much more interesting. Very much interesting, this example. I want us to evaluate the limit as x approaches infinity of 1 plus 1 over x raised to x. If you remember correctly, we said that this limit is actually equal to e, or when we're defining the number e, we said this number e is equal to that by definition. Now, can we actually use limits to actually evaluate if that is actually true or not? Or can we actually evaluate this limit and see if it is it really equal to e? Because that was actually our definition. So what we are going to do here is very simple. If I were to plug in infinity here, I would end up having 1 plus 1 over infinity. Right? So I would end up having 1 plus 1 over infinity. And then up there I would just have infinity. In other words, I would end up having 1 plus a constant divided by infinity, whether it's positive or negative. As long as it is a constant, it will always be shrinked to 0, and then I have infinity. So this whole thing now, I am getting 1 raised to infinity, and we said that 1 raised to infinity is an indeterminate form. So we are actually not getting a 0 over 0 here, and we are actually not getting infinity over infinity. So what are we going to do? And when we are plugging in, we are actually getting an indeterminate form. Sorry for that. So we are actually getting an indeterminate form. How do we end up dealing with that? So the problem we're actually having here is in the exponent. So when you are having a problem in the exponent, you want to bring it down so that you don't have a problem in the exponent. Because if we were to have infinity times infinity, we know that we are sorted because this is defined and it is just infinity. So this one is defined. The issue is when we're having an exponent, because we can either have that or have 0 raised to 0 or have infinity raised to infinite, but this one we know that it is a determinate form, so it's not a problem. This is the problem we're having, or that is the problem that we're actually having. So how can we make sure that we don't have an exponent that is giving us a problem? Because if we have a constant raised to infinity and this constant is positive, we know that this is going to be infinity, so we are fine. So we don't want to end up having 1. As long as this constant is not 1 or 0, it is positive, we know that we are actually getting infinity. The issue is when we are having a 1. Now, what is basically happening here is that we need to find a way of changing this thing that is of this type here and make sure that we are either landing to this, we are having this here. We want to either have a constant raised to infinity if possible, or end up having this one here, but this constant we don't want it to be a 1. So how can we do that? In other words, how can we change this base, or how can we change this base here so that we don't end up with a 1? So we wanted to change this base here, which is a 1, and get a different constant. So in order for us to actually change that particular base, because that base is actually giving us a 1 raised to infinity, which is a determinate form, so we want to change the base so that we end up with something that is not equal to a 1. How can we do that? We know that whenever I have e raised to ln of something here, this is the same as just that something. Or if I have ln of e raised to something there, this is the same as that something here. Bring that and then I get a 1. So we wanted to use either of these two. I like to use this one first, but if it's not working, I will try and use that. If it's not working, then I can go and do other things. So let us try and use this one here. So we end up having this is the same as the limit as x approaches infinity of e raised to ln of whatever is there here, which is 1 plus 1 over x, all raised to x. So that is what is important here, because this e and ln cancels out and we're left with that thing, which is that. But I still wanted to use it because it's gonna make sure that this one is actually moved out. So we end up having the limit as x approaches infinity, and then because that one is an exponent, you can always bring it in front of a natural log or a logarithmic function. So we end up having e, and then we have x times the natural log of 1 plus 1 over x there. We can put the brackets there, but they are not that much significant because this one is taken out. We only needed those brackets because we had an exponent to say that exponent is an exponent of everything. So once we are having that, I want you to see something here, that if I am plugging in infinity here, what is actually going to happen here is that I will end up getting infinity times, if I'm plugging in infinity here, I will get 1 over infinity, which is going to be, let me write this thing down so that you can see. So if I'm plugging in here, what I will end up getting, I'm talking about the exponent alone. So if I'm dealing with an exponent, I will get infinity times ln of 1 plus 1 over infinity, and of course this is going to be infinity times ln of, because 1 over infinity is just going to be a 0, and this is going to be infinity times natural log of 1. And you know that the natural log or a log function at 1 is supposed to be a 0. Let me prove it to you. If I'm plugging in a 1 here, you will see that you're getting a 0, or the function that is going like this is intersecting at 1, because at x is equal to 1, remember that at x is equal to 0, y was equal to 1 when we were dealing with exponential, and this one is an inverse. That's where that thing is coming from. So we are actually having infinity times 0, which is also an indeterminate form. So how do we actually change this one here such that we are not landing with this in the exponent, we land with something that we are used or something we can work with here? So the main goal of what we are actually looking for here, we are having two functions here. One function is actually leading to a 0, but I know that 0 is the same as a constant divided by infinity. So we are actually somehow having because this one is actually getting to 0, so we are actually having something like this. This one is infinity and this one here is 1 over infinity. So we are close to what we are looking for here. So why am I actually wasting time talking about these things? I wanted to explain to you something here. The function e to the power x is a continuous function. So if this function is continuous, which means that this limit, I can jump this e and then take the limit in the exponent to evaluate the limit. That is why I am wasting so much time with this, because I know that for me it is actually possible. It is actually possible to actually deal with this thing very nicely. So if you look carefully into this thing here, you will find out that we are having here infinite over that. So we wanted to change this function so that we can actually use L'Hopital's rule. So to use L'Hopital's rule, we want to have 0 over 0 or infinite over infinite. How can we manipulate this function? We don't want to change it, but we wanted to manipulate it so that we are getting a 0 over 0 or infinite over infinity. So this is going to be our e. Let me use a different color here. We are going to have e. We are going to have a limit. We're going to have x as x approaches infinity, and then once we are actually having that, so what is actually important now? What is important here is that if I were to leave this one as ln of 1 plus 1 over x, and then I divide this by x, then this function here, I have changed it to be something different than it was. But if I am changing this and say that this one is 1 over x, you will see that now, because when dividing this thing here, remember that if I have ln of 1 plus x, 1 divided by x, and then the division here becomes multiplication, and then if I'm changing this, I change the numerator and the denominator, so I will end up having x over 1, and then this whole thing will become that. That is why we are changing to this function here, because it's still the same thing. We are not messing up anything here. So we take this and we put it down. The same thing if you were you decided to say this thing here is the same as x divided by 1 over ln of 1 plus 1 over x. Is still the same thing. So you can either change this to that or change this one to that. It is still the same thing. But now, why am I choosing this one over that one? Is because when I'm taking the derivative of the denominator, it's going to require a lot from me. It's going to require what I call the quotient rule and stuff. If I'm not using the quotient rule, I need to use the chain rule to actually deal with this, and when I'm taking the chain rule, I will have to take it twice. But when I'm using this one is going to be easy, because I'm just going to use the power rule to take the derivative of that. That is why I am using this one here. Now that I am having this function here, you will find out that this is going to be the same as e raised to the limit as x approaches infinity of ln of 1 plus 1 over x, and then I'm going to divide this whole thing by x raised to minus 1. Remember that 1 over x is the same as x raised to minus 1. I just changed this. But now that you got this, is this one following L'Hopital's rule? If I am plugging in here infinity, I will end up getting ln of, and then this one is going to be 1 over infinity, which is 0. So I'll end up getting ln of 1 divided by 1 over infinity. And 1 over infinity, because when I'm plugging infinity here, I will end up getting a 0. So this is going to be a 0. And if you look at ln of 1, it is equal to 0. So I am getting 0 over 0. So since I am getting a 0 over 0, I can take L'Hopital's rule in the exponent. So that is what is important here. So I can say that now this is the same as e raised to the limit as x approaches infinity, and then I take the derivative with respect to x of ln of 1 plus 1 over x, and then I take the derivative with respect to x of x raised to minus 1, and of course this is going to be e raised to the limit as x. This one is going to be e raised to the limit as x approaches infinity. And then what is the derivative of ln? And then the derivative of ln, you can see that I know how to take the derivative of ln x, because this one is going to be just 1 over x. But instead of having 1 over x, I have 1 plus 1 over x. So what I'm going to do, I'm just going to let u to be equal to 1 plus 1 over x, and then I'm going to let my y equal to ln of u instead. So I'm replacing that thing that was sitting in the value of x by u, and then the derivative with respect to x of y is going to be the derivative with respect to of y with respect to u first, and then we take the derivative of u with respect to x. Of course, if you proceed here, you'll find out I'm looking for du of ln of u times dx of, what is my u? My u is 1 plus 1 over x, or x raised to minus 1. So if you look into this, what will be that? The derivative of u and u, we know that's going to be 1 over u, and then after that you multiply by the derivative. What is the derivative of constant? It's 0, plus the derivative of this is going to be minus x. I bring the exponent down, and then I'm subtracting a 1 from the one that was already there, and then we end up with something of this nature. 0 plus this is going to be minus x raised to minus 2 all over u. And if you look carefully here, once you have an exponent, negative exponent, it means this goes to the denominator. So this is going to be okay, let's leave this thing as it is for now and deal with u first. There's something that I'm seeing, that's why I'm doing that. So I'll end up having minus x raised to minus 2 divided, what was my u? My u was 1 plus 1 over x, and if you look carefully, 1 is the same as x over x. So this one here is going to be minus x raised to minus 2 all over, I have x and x, so it's a common denominator, and then here I have x plus 1, so I'm going to have x plus a 1. So if you look carefully into this, you can see that we are actually having something very, very, very nice here, which is minus x raised to minus 2, and instead of having a divide, I'm going to multiply, and then when I'm multiplying, I change the numerator and the denominator. So I'm going to have x here, and then the denominator I'm going to have x plus 1, and then when I'm going further, I will end up finding out that actually this one needs to go down, so I will end up having minus x, which is this x, divided by x squared times x plus 1, and then this is the same. I'm going to reduce this x and one of these x's, so I'll end up having 1 divided by x times x plus a 1. So I am actually having that derivative there. So what is happening here, the derivative of this is going to be a nice function which is minus 1 divided by x and x plus 1 here, and then in the denominator I'm actually having the derivative of this. Bring the minus down, x raised to, I have a minus 1, and then I'm subtracting a 1 again, so I am having a nice thing there. So I end up having something of this nature here. I still have e, I have the limit, I have x approaches infinity, and then if you look carefully into this, you will actually find out that I have a minus 1 over x, and then I have x plus 1. Instead of having a divide, I'm going to, let me first divide, and then we'll work it out later. I have minus x minus 2 here, and then if we are rewriting this, I can clean this up. Hope you have copied it. I'm gonna clean this thing up. So when I'm cleaning this whole thing up, I'll end up having e raised to the limit as x approaches infinity, and then here I still have minus 1 over x, and then I have x plus 1, and then I have a divide here, and then this divide here, this, I don't want to mess up, this is not looking cleaner at all, and put it here, e raised to the limit as x approaches infinity, and then I have minus 1 divided by x and x plus 1, and then I'm dividing this whole thing by minus 1 over x squared, because if I have a minus in the exponent, it means it needs to go to the denominator, which means now I'm having e raised to the limit as x approaches infinity of minus 1 divided by x, and then I have x plus 1 times, and then I'm changing this division sign here. When I'm changing the division to multiplication, I interchange numerator and denominator. So this denominator here becomes a numerator, and then this numerator becomes a denominator. And you can see now that we're actually having a minus 1 and a minus 1, so they cancel out and we'll be left with this. And also here we have an x here. One x is actually cancelling out. This x is cancelling out with one of these x's. I will be left with that x there. So what I'm going to do here, instead I will just add a page here, new page after. So I am having this here. So this whole thing is going to be e raised to the limit as x approaches infinity, and instead now in the numerator I'm just having an x, because I have this one and that one is gone, so I'll have left with x in the numerator, and then in the denominator I'm only left with x plus 1, so I have x plus a 1. And if you look carefully into this, you will find out that if I'm plugging here infinity, I will get infinity. If I'm plugging in infinity, I'll get infinity plus 1, which is infinity. So I'm getting infinity over infinity. So I'm applying L'Hopital's rule one last time. X raised to limit as x approaches infinity of the derivative with respect to x of x divided by the derivative with respect to x of x plus a 1. And if you are looking to that one very carefully, you will find out that this is going to be e raised to the limit as x approaches infinity, and then in the numerator the derivative of this, or the slope of this function, is just going to be a 1, and then the slope of this function, the derivative of this is 1, the derivative of a constant is going to be 0, so we are actually ending up with the limit as x approaches infinity of 1 divided by 1, which is just 1. So the limit of a constant, we know that it is just constant, so we have a 1 here. Therefore, the limit as x approaches infinity of 1 plus 1 over x raised to x is just gonna be e. That is where we're actually heading, which is what we usually use as a definition. Let's take 2 more examples. Maybe we would get familiar with this. So another example will be, let me use J now. So I want us to evaluate the limit as x approaches infinity of x plus 1 and then divide by x minus 1 and then this whole thing raised to some x there. Of course, if you want to deal with this, we do the same thing here. If I'm plugging infinity, I will get infinity plus 1, which is infinity. And then I get infinity here in the denominator. So infinity minus 1 is still infinity. So I have infinity divided by infinity, which is fine. But the problem, I also have infinity there. So what I need to do, I need to bring down this infinity and then see what I'm actually going to get. So what we do, we just say this is going to be the same as the limit as x approaches infinity of e raised to x plus 1 over, not just e. If I'm introducing e, there was no e there, so I need to cancel it out with natural log. So I will end up having x plus 1 all over x minus 1 raised to x. And then after that, I will have the limit as x approaches infinity of e, and then this exponent can be brought in front of a natural log. So I will have x, and then I will have the natural log of x plus 1 divided by x minus a 1. And then if you look carefully into this, the function e to the power x is a continuous function and is continuous everywhere. So I can just jump this and take the limit of the exponent and evaluate. So this is going to be the same as e raised to the limit as x approaches infinity of x times ln of x plus 1 over x minus 1. That is what is important here. But now, what is also important here is that what I want to do here is that this one here, I have infinity, I still have infinite and infinite at infinity. This is going to be infinite over infinite. I can't deal with that, so I need to sort this thing out because I can't deal with ln. Because if I was able to deal with this, then I was going to take this to the denominator or that to the denominator in the same way that we did above, but I can't deal with this. But I know that whenever I have a log function and I have x over y, I know that this is going to be same as log base a of x minus log base a of y. So I'm going to use that there, which means this is going to be e raised to the limit as x approaches infinity. And then here I will still gonna have x, but this thing here I'm going to change it to just natural log of x plus 1 minus natural log of x minus 1. Now it looks clear because this one is just 1 infinite, and I know ln of infinity just infinity, and then here I have infinite over infinity, which is fine. I actually don't have a much of a problem because I can deal with this thing first and deal with that second. I'm still gonna be sorted. So the next thing that I want to do now, I want to erase this and then finish this problem, give you a summary of what I'm actually doing, and then call it a day, because that is what is important with L'Hopital's rule. Because if you can't deal with L'Hopital's rule, then chances are your life is going to be hard when you're dealing with limits, because limits can be easy at times, they can be hard at times, but I want you to make sure that at least you understand what is actually going on here. Then now that we have this here, we can see that when I'm taking a limit of two functions, I can just multiply this and that and then take the limits separate. It's still gonna be fine, I suppose. So what I'm going to do here is this. This is the same as e raised to the limit as x approaches infinity. I'm going to multiply this with that, so I'm going to have x times ln of x plus 1 minus x times ln of x minus 1, so that I have two functions. I have two functions, this one and that one, and then after that I'm just gonna say that I have e raised to the limit as x approaches infinity of x times ln of x plus 1, and then minus, because this function here I can evaluate this as much as I want, I'm gonna split this in two limits. So I'll find the limit as x approaches infinity of x and ln of x minus 1. And also splitting these two makes my job easy, because I want to evaluate this alone, I also want to evaluate that one alone. So after that I will end up having e raised to the limit as x approaches infinity. I want this one, if I'm plugging infinity now, I can say I'll get infinity, and then if I'm plugging in here infinity, I know that I will get infinity, and then ln of infinity, we know that this function is increasing, so if x is infinite, then y will be infinite, so this is going to be infinity, and then this one is going to be infinity. So infinite times infinity, we know is infinity. Infinite times infinity is no infinity. So I will have infinity minus infinity. How do I deal with infinity minus infinity? So the best way now to do this is to, I am going to change this one here to be ln of x plus 1 divided by 1 over x, and then minus the limit as x approaches infinity, and then I'm going to change this one to be ln of x minus 1, and then I divide it by 1 over x, and we know that 1 over x is the same as x raised to minus 1, and 1 over x is the same as x raised to minus a 1. How is that going to actually help us in this particular case? Because what is important here, we want to make sure that what we are doing here is actually going to help us here. So if I'm plugging in infinity here, I will end up getting a 0 in the denominator, because I will have 1 over x, which is the same as 1 over x, and then I get 1 over infinity, which is 0. But in the numerator there, I am actually not getting a 0, so I will end up getting infinite over 0. That's not what I want. Now the second thing that I wanted to do here, if I'm checking this, I will still get the same thing, which means this. If you look at the method that we're using up there, it was very good for this, but when we are using it here, it's actually not helping us at all. So what is an alternative of actually dealing with this whole thing here, to make sure that we are actually dealing with this in a right way? Because we want to end up with 0 over 0 or infinite over infinite, but now we are getting infinity times infinity minus infinity times infinity, which is infinity minus infinity, and this is also another indeterminate form. So how do we move forward from this? That is actually now a challenge that we are actually facing. So this is what we are going to do here, because the main goal, we want to get a 0 over 0 or an infinite over infinity, and then once you get infinite over infinity or 0 over 0, you use L'Hopital's rule. But we are trying here, but we are not actually getting to the L'Hopital's rule that we wanted to actually do in this particular case. So what you actually do, you go back to what we were doing. So that is what we are going to do now. We want to go back to what we were doing. So what we are going to do, it's not that hard at all, because it's going to actually help us in a very much more interesting way here. So in this moment, that's where someone might even get stuck and be like, but why are we not following the same thing we're doing up there? Yes, we followed it. We actually did the same thing, and we ended up in this case here, and we want to see what is actually going to happen and what are we actually going to end up with here. So what is also important here is that even if, let's say, we decide to just I'm going to take this one here up, and then I want to divide, you will see something that is also much more interesting here. So instead of taking this x, splitting these two, because we'll end up having infinity minus infinity, which is also another indeterminate form, it's not like you are actually stuck. You actually moved from another indeterminate form, infinity over infinity, all raised to infinity, to actually having e raised to infinity minus infinity. That's what actually happened now. So we wanted to change that case and actually end up with something that is very useful to both to us both. So what we are going to try next is something of this nature, that we are actually going to have e, we're still gonna have the limit as x approaches infinity, and then we're just gonna end up by factorizing this here. So when we are factorizing this here, we will end up having x, and then we will have ln of x plus a 1, and then inside what will remain is going to be this divided by that is just a 1, minus we end up having an x, and then we have a ln of x minus 1, and then you divide this by x times ln of x plus a 1, and then of course this is actually what is going to remain here. So what is also important here is that I know that this one is going to be infinity, and this one also is going to be actually infinity, and then this one is going to be this, and that will end up cancelling out, and these things will be actually left here. And now if you look into this, we actually end up going to have the limit here and the limit there, and then after that this is going to be infinity divided by infinity. Still is going to be a problem, and then if you look into this one here, we're still gonna end up having another problem. Then what can actually be done to solve this problem? Because doing this is actually, we will end up taking this down there, and this one is still not solved at all. So how do we end up proceeding in this particular case? And looking into this, looking into that, you can actually see now that we are at a point whereby we are actually getting stuck. Why are we getting stuck in this particular case? Is because this is what we should have done in the first place. We should have dealt with this. Okay, let me do this. We should have dealt with that in the first place, and we could be done with this problem. But we're refusing to do it. Why? I don't know, because we wanted to get stuck. So once we are actually having this, you will see that you are actually moving back and forth in all these problems that we are having here. So once you are having these stacks, which means that there is something else that you did not do, you were supposed to do, or else there is actually the method that you are using is actually not helping you at all. So the first thing that you should have just done here is very simple. We are having x, I think we are having x plus 1, and then we're dividing x minus 1. And then after that, if you wanted to do this, one thing you can do, you can just realize that x plus 1 is just x minus 1 first. So we have x minus 1 there, and then plus a 2. So 2 minus 1 is going to be that, and then you divide this by x minus 1. Of course, this whole thing is going to be x minus 1, and then you divide this by x minus 1, and then plus, and then here we have a 2, and then you have x minus 1 because the common denominator is there. So to move here, I'm just gonna add this one because the denominator is there, and take one denominator, and then adding that will give me that. And then if you look into this part here is going to be 1 because this and that is the same, and then plus a 2 over x minus 1. If we have done that in the first place, we could be done by now, but I wanted you to see that not all these limits are actually gonna be a straightforward. But as much as you can see in the above problem that one was actually straightforward, but if you're having something of this, try and change it to be something of this nature so that you can work with it and make your life very, very, very easy. So if we are using this now and getting all the, if you are not using this, you will get stuck and you will be moving between infinity times infinity minus infinity times infinity, and then after that you can even maneuver your way out, and you will end up having infinity divided by infinity all raised to infinity, which is also not what L'Hopital's rule wants you to do. And then you will end up having infinity over infinity. Yes, you can apply L'Hopital's rule in this case, but once you have this, you are bringing it down. You will end up having one part will be infinity and the other part will be that, and now you are actually not end up getting something straightforward, so end up moving back and forth. But if you simplify this to be something so that you are not having infinity over infinity, then it becomes easy. I will show you now what I'm trying to say, and then after that I give you some of the shortcuts that you can actually think of when you're dealing with this. If the shortcut is not working, you must know that there is a manipulation that you need to do in the function, so that one of the shortcuts I'm going to give you, all of them are actually working. So what is actually happening with this is this. So this one here is still going to be the same as e raised to the limit as x approaches infinity, and then I still going to have an x. I'm not going to change that. And then this one here, we said that is going to be the same as 1 plus 2 divided by x minus 1. You saw when I was trying to show you that. And if you look carefully into this, you will find out that if I'm plugging this infinity here, I will have infinity. And if I'm plugging infinity here, I will end up having infinity minus 1, and infinity is so big compared to 1. So infinity minus 1 is going to be infinity. A constant, whether it's positive or negative, divided by infinity is actually going to be shrinked to 0. So this part is going to be 0. 0 plus 1 is going to be 1, and we know that ln of 1 is equal to 0. So now I will end up having infinity times 0, because this is going to go to 0 and this is going to be infinity. So I want to change that and change it either to infinity over infinity. In order for me to change this to infinity over infinity, I have to change this to e raised to the limit as x approaches infinity of x divided by, because this is already infinity, this is 0. To get infinity, I want 1 over 0, so that will be our infinity. So I will have 1 over ln of 1 plus 2 over x minus 1. But if I am doing this, when I'm using the L'Hopital's rule, it will be easy for me to take the derivative of that. But the derivative of this will be hard because it will require me to either use quotient rule or the chain rule twice. So I don't want to do that. Instead, I wanted to change this one to 0 over 0. So to get a 0 over 0, this one is already 0. This one is infinite. So the one that has infinite, I wanted to go to the denominator. That is why I'm not going to go this route. I am going a different route, which is going to be ln of 1 plus 2 over x minus 1 divided by 1 over x. That's what I want us to actually go to. I hope you can see this thing. I'm not doing it to confuse you. I want you to see that if you don't follow these principles the right way, you will actually be moving back and forth with these limits and you're not gonna end up anywhere. You just have to follow the principle as it is. And even if you switch these things around, mathematically it will be correct, but it's gonna give you a derivative that is hard to work with. It's not like it cannot be done. It can be done, but we also want to make things easy for ourselves. So this thing here, we know that this is going to be infinity. 1 over infinity is going to be 0, and this one is going to be infinity. 2 divided by infinity is going to be 0. 0 plus 1 is going to be 1. Ln of 1 is 0, so we're having a 0 over 0. And then once we have that, we just say that because we have a 0 over 0, we can use L'Hopital's rules and say this limit is going to be the same as the limit as x approaches infinity of the first derivative with respect to x of ln of 1 plus 2 over x minus 1, and then you divide this whole thing by the derivative with respect to x, and in the denominator here 1 over x is the same as x raised to minus 1. That is what is important there. And then if you look carefully into this part here, you will find out that this part here is just the same as 2 times x minus 1. 2 times x is going to be 2 times x minus 1 all raised to minus 1. Right. So we wanted to take the derivative of this. I will try and make sure that, because you can see that instead of having an x here, whereby if we had x, ln of x will be just the same as 1 over x, and then if you are having that, you would find out that we'll be able to deal with it. But instead of having an x here, we're actually having something else, which is 1 plus 2x minus 1 raised to minus 1, and then this whole thing here is the same as what I'm going to say. Let's just let u to be equal to that thing, and then once we use that thing, we'll be able to take the derivative of that numerator there. I will try and be as fast as possible so that I don't end up wasting much more time, because this video is already long. So here I will have e, and then I'll have the limit as x approaches infinity, and then of course what will be the derivative of this? The derivative of this is going to be 1 over what is inside, which is 1 plus 2, and then I have x minus 1 raised to minus 1, and then times the derivative of what is inside, which is this. The derivative of this is going to be 0, and then the derivative of this, I'm gonna pull out the 2, and then the derivative of this whole thing is going to be, I'm gonna bring out a 1 and then multiply by x minus 1, and then subtract another 1 to have a minus 2 there, times the derivative of what is inside, which is just going to be a 1 there. So derivative of this of x minus 1 is just a 1. So that is what we are going to get inside. We have 2 times minus x, and then we have x minus 1, subtract a 1, and then we have that. And then this whole thing we divide by the derivative of this is going to be minus x, and then minus 1, or just a minus 2. So that's how we actually end up with this. I have e, I have the limit as x approaches infinity. Then we are trying to clean this whole thing up. So we will end up having 1 over 1 plus 2 times x minus 1 raised to minus 1, and then inside we will end up, this is 0 plus this, so we'll end up having minus 2 times x minus 1 raised to minus 2. So that we get what we are getting in the numerator, and then in the denominator we're still having minus x raised to minus 2. And then let's hope now that things can actually work out. We need to simplify this a little bit. How do we simplify it? This is not going to be a little bit easy. Let me try. I'm going to have e, I'm going to have the limit, I'm going to have x approaches infinity, and then here we'll end up having 1 divided by 1 plus 2 divided by x minus 1. And then I'm still focusing only on this part, so I'm going to focus on this and then focus on that and see what we are getting. So this whole part here, 1 is the same as x minus 1 divided by x minus 1. And then after that, this part here is going to be the same as the denominator is the same. So I'm just going to add these two things. So when I'm adding these two things, I will end up with something of that nature, and actually one denominator, which is x minus 1. That's what we are actually getting here. And then we go to this part here. This part is going to be minus 2 divided by x minus 1 all raised to a 2, because I'm taking this to the denominator. And then the denominator is minus 1 over x squared. And then once we are having that, we still have e, we have the limit as x approaches infinity. And then after that, you will see that I'm going to change first I wanted to, let me change this one first. This one first to multiplication. So I will end up having 1 times x minus 1 divided by x minus 1 plus a 2. And then this one, I'm still going to keep it as minus 2 divided by x minus 1 squared. And then I still have this big denominator, which is minus 1 over x squared. And then now what I'm going to do, I'm going to change this one to e raised to the limit as x approaches infinity. And then, of course, 1 times anything is still that one thing. And then what we are going to do here, I'm still going to try and fix this one and see what we're getting. I have x minus 1 divided by x. X minus 1 plus 2 is the same as x plus 1. Yes. And then multiply this by minus 2 divided by x minus 1 whole squared. And then this whole thing, I'm going to change it to multiplication. The denominator becomes a numerator and the numerator becomes a denominator. And then once you have that, you will find out that now some nice things will happen. This one will cancel out and one of these will be gone. And then I will have 1 times minus 2 times 2x squared. So I'm still going to have an e. I'm going to have the limit as x approaches infinity. And then here we'll have minus 2x squared. And then I divide this times that, I will have a minus 1 times x plus 1 times x minus 1. And if you look carefully into this, you will find out that this is the same as e raised to the limit as x approaches infinity of, we have this minus and this minus, they cancel out, so we end up having 2x squared. And then after that you have this. So when I'm expanding this whole thing here, I can see that this one is going to be x times x. Remember that this minus and this minus, they cancel out. I will end up having x squared, this one times that, and then minus x times 1 is going to be x, and then I multiply this one and that, I get this, and then I multiply this plus 1 and x, I will get a plus x, and then I multiply 1 and a negative 1, I'll get minus 1, which means this one and that one cancels each other. So we end up having x squared minus 1. So in the denominator, we'll end up having x squared minus a 1. And then if we're plugging in this infinity here, we'll get infinity squared, or infinity times infinity. Infinity times infinity is infinity. Infinity times 2 is infinity. So in the numerator, we're getting infinity. In the denominator, I'm plugging in here, we'll get infinite squared, or infinite times infinity. Infinite times infinity is infinity. Infinity minus 1 is still infinite, so we're getting infinite over infinity. So once we are getting infinite over infinity, we can apply L'Hopital's rule once more time. So we'll end up having e raised to the limit as x approaches infinity of the derivative with respect to x of 2x squared, and then all over dx of x squared minus a 1. And then if you're looking into this, this is supposed to be e, and then we still have the limit there, a nice limit as x approaches infinity. And then the derivative of 2x squared, we know that we're going to bring this 2 and it arrives to this 2, so we end up having 2 times 2, which is 4x, and then squared is still going to be 2 minus 1 is going to be just a 1, so we have a 1 there. And then the derivative of this, of course, is going to be a 2x, and then here bring the 2 down, and then have an x to separate a 1. We're just going to have a 1. And then, of course, if you look here, the derivative of a constant is always going to be a 0. Hence, we are having e raised to the limit as x approaches infinity of 4x divided by 2x, and x they cancel out. And how many 2's out of 2? So x and x, they cancel out, and now we're left with 4 over 2, and 4 over 2 is the same as a 2. So what is the limit of a constant? It is that constant. So we have e raised to 2. So that is the final limit that we're actually having here. Again, just to give you a quick summary here, you know that when we're dealing with this example here, we worked all the way, we found it by just making sure that we change this base because we are getting a 1, and then we changed it, and then we got something better, which is of this type. And then after getting whatever we're getting, we need to introduce e. When I'm introducing a e, there was no e there, and then we use ln to cancel it out so that we can bring this one down. And then after bringing it down, we notice that we get infinity times 0. So once you have infinity times 0, is easy. Infinity times 0, that is fine. You either change this and leave this, you change this to 0. So infinity, you know that infinity is the same as 1 over 0. So that is what is happening. So what you actually do now, you just decide that I'm going to keep the function that have a 0, and then this one I end up saying 1 over that function. So, and then you deal with your derivative of the numerator and denominator. You do it twice, you simplify, you will get this. The same thing here. What I wanted to show you with this example is that if you just decide that, okay, I'm going to bring this down, I'm going to use this e like that, it is fine up to a certain point. But once you proceed, you can't proceed because of what is happening there. I remember actually when I was doing these things for the first time, when I was having one of these limits like this, I would get stuck. That is what actually happened when I was doing this for the first time. And if, let's say, you are doing this in a test and you don't practice it, that's what is going to happen to you in a test, and you will think that the problem is wrong. Actually, the method that you are using, you need to be careful, because what we want to end up with here, want to get a 0 over 0 or infinite over infinity. Once you get infinite over infinity, and then you have infinity up there, or you are having a 0, then there is something that need to be done inside here. That is why this one needed to be changed here. But I had to show you that if you are doing your own thing, you might getting stuck and think of otherwise, but I wanted you to see that. And then of course that will actually be the end of this problem, because we actually ended up getting this, and we said that the limit as x approaches infinity of x plus a 2 all over x minus a 1, and then you have an x there. This must be equal to e raised to a 2. That is what is important here. So I want us to actually look at the summary of these things, and then I will actually let you go, and please copy it so that you don't end up wasting most of your time. So first of all, we talked about indeterminate, this is a D, indeterminate forms. So we had some indeterminate forms, and then of course if you have 0 over 0 or you have infinity over infinity, so all you have to realize here, let's say you wanted to evaluate the limit as x approaches some value a of some h of x. So if we are getting 0 over 0 or infinity over infinity, this implies that your h of x is actually equal to some function f of x divided by g of x. Of course, if you are doing that, it is also easy that you can just say that the limit as x approaches some value a of that h of x or of f of x divided by g of x is just gonna be the same as the limit as x approaches a of f prime of x divided by g prime of x. So that is what we were actually saying, that we just need this, and it's okay, we just use the L'Hopital's rule right away. So if, let's say, in this particular case you are getting a 0 times infinity, what do you need to do? What you need to realize here is that your h of x, which is this function here, is actually equal to some function f of x times g of x. We have two functions being multiplied. So your goal here is very simple. You want to make sure that you actually change this to be either that or that. And in order to do that, you can see that this function here is going to be a 0. And you know that 0 is just the same as 1 over infinity. So once you are here, you are already close here or there. So what you basically do here is this, is that what is actually supposed to happen is here is that you want to convert this to be actually a function. If you want infinity over infinity, this function infinity here belongs to g of x, so you're gonna keep it as it is, and then you wanted to change this 0 so that you get infinity over infinity, so you will say it's 1 over f of x. So that is what you do. Or you can change this one. So this root here, so for this one here, you are actually going to you want to get infinity over infinity, but this one here you want to actually convert now to 0 over 0. I will explain here what is happening. Like I said in the example here, you are still having a function times another function, so you have some f of x times g of x. So this function here, you can convert it to be, if you want a 0 over 0 like this, so the function here that is having a 0, keep it. So here you have f of x, so you will keep your f of x and divide by 1 over g of x. So you can either convert it to this or you convert it to this, depending if you are looking for this one or that one. Which one do you have to choose? Choose the one that is not going to give you a difficult derivative. Choose that one. So that is what is important here. You can see that in the previous examples, the last two, we're actually going with something kind of close to this in the exponent. But now, what do you do? Remember that after this, you will have to take the derivative. Remember this is bigger. You will take the derivative of this and take the derivative of that and then take the limit. Here, you will take the derivative of this and take the derivative of that and then take the limit. And if, let's say now, when you are evaluating, you are actually getting infinite minus infinite. So what is important here is very simple. This one here, once you get infinite over infinite, infinite minus infinite, it's not always gonna be very straightforward, because of one thing here. You can decide, I'm gonna show you this thing here, because some people usually say that you do this, but it has its shortcomings. I will tell you now. So this means that you have some function f of x minus some function g of x. And then to actually deal with this, what most people usually say, they say that factor out this f of x, and then after factoring it out, here you will be dividing f of x divided by f of x, you'll have a 1, and then here you will end up having a g of x, and then here you will end up having an f of x in the denominator. And then after that you have this, and then you can decide and say, I am going to place it in the denominator, something like this. Okay, this one here is always going to be true, and that is actually a good way of dealing with this. It's going to be true that you are actually going to get something of this nature and also get this. But the problem that we are actually having here is that not always that this one can actually be done, because if, let's say, this one was going to infinity, you will find out actually that this is going to be infinity, this is going to be infinity, and infinity over infinity is also an indeterminate form. And then we have 1 over infinity, we'll get a 0, and still we are not getting anywhere because we have another indeterminate form that we have created. So this route here, I don't usually recommend. I usually recommend that if it happens that you are getting something of this nature, what you need to do, it might happen that you are actually having a function somewhere here that need to be manipulated. Manipulate it in such a way that what is actually going to happen inside will be something that is going to be useful to you. So here, what I usually say is that what you can do is this. I will say this one here because it's not specific. Manipulate the part that is giving you a problem. This one is not really specific because you saw that what we're trying to do here, we just rewrote the function, and then after rewriting that function, and then we got a hyperbolic function, and then from that hyperbolic function we were able to actually deal with the limit. So this one is not specific, but what is actually specific is when you are dealing with polynomials or rational functions, and sometimes when you're having algebraic expression, all you need to do, you just need to factorize the highest power. You factorize the highest power. Sometimes when you are factorizing the highest power, you will be able to actually eliminate the part that is giving you this. For instance, if let's say you are having a rational function of x cubed minus 2x plus a 1, and maybe you are dividing this by 2x squared plus 3x plus 7, you can just say that, okay, the highest power between the denominator and the numerator is actually going to be x squared as x cubed, but we are not only factorizing the highest power in both, we are factorizing the highest power of the denominator. So if you are having a denominator, in that case you just factorize the highest power of the denominator if you are having rational functions. Another way to look into this, if you are just having functions, if f and g are, let me just say they don't have denominator, do not have denominators, what you just try to do, try and factorize the whole function. So that you are left with plus or minus infinity plus or minus a constant times plus or minus infinity plus or minus a constant. Why am I saying that? Is because we know that if we are having infinity and then we are comparing it with a constant, infinity is always going to win because it's so big. That is what you are trying to do. For instance, if you were looking for the limit of x cubed minus x. So what you need to do here, because you will have infinite times infinite times infinite, which is infinite minus infinite. What you need to do here, you just end up having to factorize and take out the common factor x, and then you'll be left with x squared minus 1, and this one is going to be infinite minus a constant, and this one is going to be infinite, and then this one is actually going to just tell you right away that you are actually having infinite times infinite, which is infinite. So that is the kind of factorization that I'm talking about here, that try and factorize the whole function. Here this is the one that we started with in the beginning. So this one is kind of a little bit difficult to just simplify out, that you can either go this route or go this route. But sometimes if you are trying to do this, in most cases when you're doing this you get stuck. I usually say try and manipulate this one, is more powerful. But when it comes to this part here, sometimes this one is always going to be easy. You can just deal with it. Of course, this one you can even deal with the L'Hopital's rule straight away. This one here is the one whereby L'Hopital's can't be used, but you need to factorize. Maybe you'll be able to see what is happening. And then the last three is when you are actually having a 0 raised to a 0. This one, what it means that you are actually having h of x, and h of x is equal to some f of x and all raised to another function g of x. So how do you deal with this particular case here? All you need to do here, you must always change it to e raised to ln of f of x all raised to g of x, so that you will end up having a nice thing like e raised to g of x times ln of f of x. So because this function is a 0, you know that this one is a 0, and then this one here, when you're plugging in a 0, when you're getting closer to a 0, a ln function usually goes like this. So as you're getting closer, it's going to negative infinity. So you know that you already have infinity somewhere here. It doesn't matter whether it's negative or positive, it is infinity, associated with infinity. So this one is going to be infinity, and then here you have a 0. So if I have a 0 and I have ln, I want ln to be always in the numerator. So this one you will end up having to change it to e raised to ln of f of x divided by 1 over g of x. So that is what is important. So change this to this, and then if you are having this indeterminate form 1 raised to infinite, then it means that you are also having h of x, and h of x is still the same as f of x raised to a g of x. And if you look carefully into this, you will actually find out that this one here, remember that in this case, the reason I don't want to deal with ln, because I will end up having to take the derivative of ln times the derivative of this. So if it is in the denominator, I will end up having to take 3 derivatives, 2 chain rules. So I rather have this one. It's going to be easier if I'm dividing with it. I hope you get what I'm trying to say here, because this whole thing is also saying that you need to change this to e raised to actually ln of f of x divided by 1 over g of x. Let me see this, what is actually basically going to happen here. How did we end up with this whole thing? But it's straightforward, because I have this one here. This is approaching 1, and this one is actually approaching an infinity. So if this one is approaching this one is approaching 1, so ln of 1, we know ln of 1 is just going to be 0. So in the numerator we'll have a 0, and then in the denominator this one goes to infinity. So 1 over infinity is 0, so I have a 0 over 0, so it's still fine. And then the last one is going to be, if you are getting infinity raised to 0, of course you do the same thing here. You had your h of x, which is equal to some f of x, and then this is g of x. So this whole thing is equal to supposed to change it to e raised to ln of f of x, and then you divide it by 1 over g of x. So 1, 2, 3, they use the same thing here. Of course, this is the summary that I use when I am actually dealing with the laws of when I'm dealing with the L'Hopital's rule, and I wanted to use L'Hopital's rule other than other methods. And of course, these methods are only useful if you are having 0 over 0, use L'Hopital's rule. Infinite over infinite, just straightly use L'Hopital's rule. If you are having 0 times infinity, I'm always telling you that use L'Hopital's rule. But if you are having this one here, if the function can be manipulated, I usually say that go for L'Hopital's rule after you have manipulated the function. But in most cases, I always say that try other methods if they are possible, and then this should be the last method that you try. And then if you are actually having this one here, or that one there, or that one, I always say use L'Hopital's rule. That's where we are actually going to stop. And of course, this was a little bit long, especially given that the number of exercises. But I hope with the 2 questions that I added are actually going to give you some clarity of some of the challenging problems that you can simplify by knowing what you are doing here.